Welcome to Hot Chips 2024. Tutorial 1. AI-assisted hardware design.
I know it's early. Thank you all for being here on a beautiful Sunday. We appreciate your interest in this topic. So please come on in, make yourselves comfortable, plenty of room. It's nice to be back here at Stanford in Memorial Auditorium. My name is Bryan Chin, and I'm heading this tutorial session this morning, which is about AI and chip design. So what kind of motivated this? So I was looking for graphs to show this morning, and there's tons of information. I couldn't find something that really articulated what I wanted to show, but I found the graph, which was generated by AI, which shows a hockey stick, right? And it's a traditional hockey stick. If you talk to someone in marketing, they're like, oh, this is a hockey stick. But this one's really interesting because it shows the amount of training flops going into AI models. And if you notice, the vertical axis is actually logarithmic. And so if you look at, with the introduction of ChatGPT to the public 2 years ago, we're looking exponential on an exponential axis. So the amount of computation going into training is pretty incredible, which kind of leads to this question. So when I started in the program committee, let's see, a couple months ago, probably back in January, I think it was. We're entertaining a lot of papers and topics about AI chips, and you'll see at this conference there's a lot of talks about chips for AI. So we've been designing chips for AI for a while, and the question that came up is, well, how do we actually use those tools to design those chips? How do we eat our own dog food, if you will, right? And so that motivated this talk. Is like, I didn't know a lot about this topic, but we found 4 experts in this field to kind of give us a background on what is the state of AI today and how can it be used to design chips. So with that, I'm going to go over what we're going to talk about today. So our first speaker is Mark Wren. Mark Wren is the Director of Design Automation at NVIDIA. He focuses on machine learning and GPU tools to accelerate chip design. And he has more than 20 years of experience working in research at both IBM and NVIDIA. He's got more than 30 patents, more than 100 co-authored papers in this topic. So he's very qualified to give us kind of an overview of, well, what is the state today of AI? How is it used in many different applications in chip design? Next, we have Stelios Diamantidis. He's a distinguished architect of Synopsys, and he's leading the Synopsys AI technology strategy since its founding in 2017. Stelios is going to talk about some of the more traditional AI techniques. How has AI been used, and tools that we use today. Right? You may not even know that behind some of these tools, AI techniques are being used. And then we're going to go from kind of mature technologies to kind of less mature technologies. So I have these color bars there. We're starting with kind of older technologies and migrating our talk to newer ones. So the next up is going to be Hans Bouwmeester. He's the COO at PrimisAI, which is a startup which is specifically targeting large language models, which we've all heard about and used, in the area of chip design. Hans has more than 2 decades, more than 20 years of experience in kind of this field, and he'll be going over the basics of LLM and RAG, Retrieval Augmented Generation. Next, we have Hanjin Zhuang. She is a 5th-year PhD student at UCSD, where I work. Her advisor is Jishen Chen, and she's going to describe how we use LLMs and adapt them, so adaptive techniques for LLMs for chip design. And she'll go over some of the latest research in that area. I should mention she has been recognized by the ML Commons, which is a benchmarking organization for machine learning, as one of the rising stars in this field. By the way, Hanjian is graduating this year, so she's also in the job market. So if you're interested in talking to her about that, I'm sure she'll be happy to talk to you. And finally, we're going to have Mark come back out and talk about some of the latest things in using AI for chip design, and that's LLM agents. That's having multiple LLMs kind of cooperate and talk to each other at a very high level of abstraction. So I hope you enjoy this talk. Time permitting, and we're very tight on time. Apologize for that. We have a lot of material to go through. We'll try to do a Q&A. If we run out of time, be aware there's always a Slack channel, and we're going to monitor that for the next 24 hours. We'll also be available at lunchtime to answer questions. So what are the takeaways? Well, we want you to be able to come away from this talk with what kinds of tasks is AI well suited to today, and where is it going, right? We have this teasing question, will AI elevate or replace hardware engineers? I'm not going to answer that question. I'm not brave enough to answer that. But what I want you to take away from this talk is, well, what do I need to learn more about so that I can try to answer that question myself? Okay, and with that, I'm going to bring out Mark for the first talk. Thanks.
Good morning, everyone. And thanks, Bryan, for a nice introduction. I'm honored to open this tutorial with an overview of AI for chip design. So in this talk, I will cover some of the key AI techniques that can use in chip design, and I'll also show their real applications. Obviously, I cannot discuss too many details in short 30 minutes, but hopefully I can give you an overview on what is possible, and so you can imagine how to apply AI to your own work. First, what is our motivation, right, to do AI for chip design? We want better design performance and better design productivity, right? Performance and productivity. So how can AI help? I think there are three categories of tasks that AI can help. First is analysis, and second is optimization, and third is assistance. The analysis and optimization tasks are very familiar to designers because we always first analyze what's the performance of the design. Then we can optimize these designs. The assistant task is relatively new. It is only enabled by language model. So for analysis, AI can help we analyze the chips faster and make predictive analysis, which is often cross design stages. For example, predicting the physical design stage effects in synthesis. For optimization, AI can help make optimization run faster, scale to larger design problems, and achieve better quality results. And for assistant, AI can assist designers with design know-how, help designer coding, and automate manual design tasks. So at NVIDIA, we would like to build AI to build a chip for AI. So over the last 6 years, we have done many AI for chip design research projects. Many of these projects are in production use today. Our project covers a wide spectrum of design areas, such as architectural design, RTL, verification, synthesis, cell design, physical design, including placement route and optimization, as well as analog design and lithography. I believe this is a representative of what's possible with AI today. We started with AI for design analysis type of applications, and then transitioned to AI for design optimization, initially with RL, reinforcement learning, or some of the black box optimization algorithms such as Bayesian optimization. Later, with generative AI models. And recently, we have been working on AI for design assistant projects using language models. So in this talk, I will cover some analysis and optimization projects. In the following talk given by Haishan and me, we'll cover more design assistant projects. Okay, so in the rest of the talk, I'll cover some of these key AI techniques used in design analysis, optimization, as well as assistance. For each technique, I will first explain some basics, and then I'll demonstrate one or two applications of the technique in the real designs. So let's get started. For design analysis, let's first look at the classical machine learning techniques, such as classification and regression. These techniques, including things like linear regression, supported vector machines, decision trees, neural networks, they are very suitable for applications that have small amount of structured data and often requires hand-tuned feature engineering. Unlike classical machine learning technique, deep learning technique can handle large amount of data and they usually do not require feature engineering. Let's pay attention to two main deep learning architectures: convolutional neural network, CNN, or graph neural network, GNN. So CNN achieved huge success in the image domain. Since lots of physical design data have these 2D features, we believe CNN is very suitable for physical design problems. GNN was originally proposed to handle social network graph. Chip design netlist or circuits have graph structure as well. Therefore, GNN is very suitable for netlist and circuit learning. The first example I want to show is a design analysis problem, which is using AI to predict IR job. This application demonstrates the capability of AI for fast analysis than conventional analysis tools. So IR job is a very important analysis in physical design. It often takes hours to solve because it needs to solve billions of variables in a system of equations. Fast IR job analysis can enable fast physical design optimization with this fast analysis in the loop. So we would like AI to predict IR job from cell-level features, such as internal power, leakage power, and so on and so forth. So first, for each time step, we can create a two-dimensional power map based on these all features. Then we feed this power map for all the time steps to a CNN model, which will produce a map of coefficient. And this coefficient will be used in a linear regression to fit the cell-level features to the cell-level IR job. Then we can produce the final IR job map based on all the predicted IR job on each cell. Note that here, instead of directly predict the IR job map, we combine a CNN model with a linear regression model to predict the IR job at the cell level. This gives us better model transferability. And this method can achieve over 94% correlation with ground truth, but only needs 3 seconds to simulate, as compared to 3 hours of running commercial tools. The second AI application for design analysis is layout parasitics prediction. This application demonstrates the capability of AI to perform cross-stage analysis. So in analog design, the designers often start with schematic design, and then they have to draw the layout. The designer has to consider the layout parasitics effect when they design a schematic to achieve the design goal. So can we use AI to predict the layout parasitics even without the layout? Because the layout process is very time-consuming. So if we actually have a large data set of previous design schematic and the layout, then it's possible to train the AI model to do this. So here we leverage GNN as the model. The schematics are converted into heterogeneous graph, and then this graph have devices and the nets as nodes, and their connectivities as edges. Now apply GNN, it can make predictions on the net nodes to predict the parasitics capacitance on that net. And the right figures shows the prediction results as compared to the ground truth. And using this kind of prediction, we can achieve simulation errors less than 10%. So next let's discuss AI for optimization technique. The first technique is Bayesian optimization. It aims to optimize a black box function. For example, maximizing this function f of x without knowing detail of the f. It optimizes this function by iteratively sample x and evaluate fx. And after a number of trials, it finds the best x it's sampled. And the trick is to figure out how to sample at each iteration. This is done by a learned model. With this model, it can sample the most promising data points at the next iteration, which can most likely give the improvement for the objective function. And it will update the model with every new data point using this Bayesian principle. So Bayesian optimization is very often used to parameter optimization problems. Here, let's look at the macro placement parameter optimization problem. So macro placement is a very important design stage that has huge impact on physical design quality. It is often done manually, which takes a long time. That is why it is a favorite design problem for AI researchers to work on. So here we can actually like to use GPU accelerated placement to do macro placement. We notice that the placement tool have many parameters that has huge impact to the macro placement solution, as shown in this animation. So there are a lot of placement parameters, and we can on the left figure we show all the placement parameters. So we apply Bayesian optimization to find the best placement parameter efficiently, because so many parameters have very large design space to search. It is also a multi-objective optimization problem, since we need to simultaneously optimize wireless, congestion, as well as density. And we show that with Bayesian optimization, we can find a very good design points. It's using the open source GPU accelerated tools often leads to better quality than commercial tools, actually. So next, let's look at the another AI for optimization methods, reinforcement learning. So in reinforcement learning, an agent interacts with the environment. The agent can send the action to the environment, and then you observe the state from the environment. Also receive the rewards from the environment. And the goal of the agent is to maximize its received reward. If we can convert our optimization problem into reinforcement learning problem by letting it optimize for the objective function as rewards, and also convert our optimization variables as actions for the agent, then an optimization problem can be solved with reinforcement learning. So we'll show a couple of applications for reinforcement learning in design automation. The first application is using reinforcement learning to fix DRC errors. And this animation shows an RL agent fixing DRCs in a standard cell layout. The red dotted lines are DRC errors. This application is actually used inside a standard cell layout framework called NVIDIA to design cell layout automatically. The action of the RL agent is to add an additional M0 grid to the layout. And the state of the environment is the current layout image, while the reward is the number of DRCs reduced after each episode. As shown in this sequence example, start from 6 DRCs. The RL agent can insert one M0 grid at a time and eventually fix all the DRCs, which receive a total of 6 rewards. This agent model is built on CNN. It can recognize the DRCs and layout patterns. So the second reinforcement learning application is data path optimization. Data path quality is very important to GPU, since there are many computing data paths on the GPU. Prefix adder is one of the most important data paths for us to optimize. There are many no prefix adder structures, such as Slansky, Cogistone, and so on and so forth. Can AI find a better prefix adder structure? Now, if we formulate this as a reinforcement learning problem, the action for the RL agent is to modify the structure as shown in the animation. The state of the environment is the current structure, and the reward is the area and the delay change after synthesis evaluation. So it turns out RL is capable of finding better results than these well-known structures, and even better than some of the optimization methods, such as simulated annealing. And the delay area curve on the right shows that the RL agent generates a better delay area trade-off than the other methods. Now let's discuss exciting new ways of performing design automation using generative AI. Generative models trained on a large amount of unlabeled data can learn its data distribution. Therefore, it can generate new data points in this data distribution. A well-known generative AI model is Transformer, which can learn to generate languages. For example, conditioned on the sentence of an input language, it can generate a corresponding sentence on an output language. So we can apply the same generation principle to optimization. If we train a transformer on an optimized data set, it can generate optimized data points given unoptimized data points as inputs. Furthermore, generative model can be used to learn a representations of the data, so-called latent space, which is often had a low dimensional space than the original data. This is learned by models like variational autoencoder, VAE. With AAE, we can learn the latent space of data, and optimization on this space is more efficient. So let's discuss an example of the first use case of a generative model. Optimizations of timing and power in physical design is the most time-consuming step in the design flow. We often cannot scale the design to a bigger design space just because optimization takes too long, days. We often cannot, if we can use AI to improve the speed of this optimization, we can scale the design bigger and achieve better PPA. So we investigate one of the main optimization transform called the gate sizing. Let's consider all the combinational gates on a timing path. And each gate has its own physical and electrical features, such as T0, T1, T2, all the way to T4. And our goal is to predict its optimized gate size, such as S0, S1, all the way to S4. So if we treated this list of gate features as input sequence, and the list of the gate size as output sequence, then we can apply a transformer, right, to model this. And interesting, the output size of the transformer should not be conditioned only on the input gate size features, because we need a desired power delay trade-off. If we just size the gates to any size, then the power will be too much for us. So we need to condition this generative model on a power delay trade-off variables. And we achieved very promising results on this work. It effectively speeds up the gate sizing by hundreds to 1,000x compared to commercial tools. So similar technique can also be applied to other optimization transforms. So the second application of generative model I want to show is about accelerated design space exploration. This application shows the effectiveness of representation learning for optimization. So the challenge of design space exploration for accelerated design is that the design space is often high-dimensional, multi-objective, and very costly to evaluate. It also often has an irregular landscape, as shown in the picture. So if we can make the design space smooth and reduce its dimension, it will be helpful for optimization. And this is achievable with variational autoencoder. In addition to using the variational autoencoder to learn this low-dimensional design space, it also adds an additional loss function to predict design performance given the latent space. Then, together with this predictor and this latent space, we can apply the Bayesian optimizations or reinforcement or gradient descent methods that I mentioned before to optimize this latent space. And final result shows very good sample efficiency and better quality. We believe this learning latent space can be applied to many design problems which has high-dimensional optimization space to consider. Last, but the most important AI techniques for chip design is language model. So we all know language model is good at question answering, coding, extraction, rewriting, classification, summarization, and reasoning. Now, compared to the previous AI techniques, LLM is a generalist. Because it's trained on a very large amount of data, it can do many things. So we can directly use a language model without any training. Unlike previous AI techniques, all require some sort of training on your own data. Therefore, LLM has the broadest applicabilities in chip design. The question is, how do we make LLM learn to do some special things in chip design we do? Because we often have special knowledges that's not included in the pre-training data for these LLMs. There are 3 ways to incorporate this actual design knowledge to LLM. The first is in-context learning. By adding design knowledge to the prompt context, LLM can learn a new knowledge on the fly. And very commonly used in-context learning technique is called retrieval augmented generation, or known as RAG. So Hans' tutorial will cover these techniques in detail. Second is parameter training. When we have a large amount of domain data, we can adapt a foundation model to this domain by continual pre-training or supervised fine-tuning. So in the ChipNeMo project, we collect 24 billion tokens of chip design document and code and train our own model based on off-the-shelf foundation models. Haixian's tutorial will cover more domain adaptations in detail later. The third method is agent. Agent use tools, memories, and planning capabilities to learn chip design domain scale without fine-tuning. I will cover the agent application in the last tutorial. So we have seen an explosion of novel language model use cases for chip design. This figure shows the distributions of language model use case for papers appeared in the recent LLM design conference. Although RTL generation is the main use case, there are lots of other use cases such as test bench generation, EDA chatbot, copilot, documentation, HLS generation, HLS debug, assertion generation, defect analysis, hardware security. And this is just one conference, and every day many new LLM papers on chip design domain are published on arXiv. So I think we are experiencing a Cambrian explosion of diverse LLM applications for chip design. By the way, next year, LLM Design Conference, IS-led, will be held at Stanford as well after DAC, so welcome everyone to join. So as I pointed out earlier, LLM applications for chip design is in the form of systems. So if we take all the applications showed in the previous slides and put it into 3 buckets, these 3 buckets are a know-how assistance, coding assistance, and task automation assistance. So coding assistance help generate design and verification code, right? Such as RTL, test bench, EDA script, config files. Know-how assistance help generate insights, knowledge, ideas, answer questions about your design, tools, and the infrastructure, so on and so forth. Task automation assistance can be further divided into 3 categories: analysis task, optimization task, and debug task. So analysis tasks or analysis assistance helps with designers to do summarization, report log analysis, visualization of design and related data, checking for rule violations, and so on and so forth. The debug assistance helps with designer to triage and fix a design problem, such as a regression failure in your logical design or timing failure in physical design. Optimization assistance helps designers to optimize design and verification. For example, architecture exploration, recipe optimization, or like coverage closure. So let me show some example for coding assistance for EDA script generation. Here, we use ChipNeMo to generate VLSI scripts. It can generate script for both internal VLSI tools as well as commercial VLSI tools. The internal tools is based on Python, while the commercial tools is based on Tcl. this is another example on how know-how assistance works. We build an engineering chatbot to provide the knowledge to designers. The users of this chatbot can ask it any design questions about infrastructures or tools, and they can support general design problems as well as internal design tool usage problems. Finally, this is the example of analysis assistance. It's called for bug report analysis. So every product design team has their own bug checking system. The bug report is often long and very difficult to read. So a summary of bug report would be very helpful. Also, additional analysis, such as who should be assigned to this bug next time, and let's search for similar bugs, can be also useful for design productivity. And this can all supported by LLM. So here haven't talked about the optimization assistance or debug assistance, but we'll cover some of those examples in the agent tutorial. So finally, here's my closing thoughts. I think optimization techniques such as Bayesian optimization and reinforcement learning will continue to drive better PPAs for chip design. And the generative AI trained on optimized data, right, can actually be used to speed up traditional optimizations by order of magnitude. I think this is a very new directions that the EDA tool vendors should look into. And language models and agents can significantly improve chip design productivity by providing design assistance such as chatbot or copilot and automating more manual design tasks. I want to emphasize one important issue in applications of LLM for chip design, which is the importance of reliable and efficient inference infrastructure. It is one thing to do research POCs with some inference engine. It's another thing to serve hundreds, thousands of designers daily without a downtime using a academic inference engine, right? So productionized inference engine, reliable and efficient, is very important. And I want to finally take this opportunity to call for action. This LLM is so useful for chip design, but we don't have a lot of data sets or benchmarks out there to help research community to come up with new ideas and evaluate their ideas. So if we can create more data sets and benchmark, it will be very helpful to move this field forward and benefit everyone. We have been working on benchmark efforts such as Verilog eval and the formal verification eval, and also datasets efforts such as LLM for hardware design to collect training datasets for RTL. But I think this takes a community to build this effort. And that'll be all. Thank you for your attention. And next, we'll have Stelios for Synopsys to give a tutorial.
Thank you for joining us today on a Sunday and taking personal time to join the tutorial. And I think Mark gave us a very nice overview of the AI-assisted design space. I'm going to then double-click on a number of topics that Mark mentioned and then add a few more insights on top of that. So my talk is going to be focused on optimization. Optimization, if you'd like, is a little bit of a rear-view mirror at this point in time in AI-assisted design, because it's a technology that's actually made it into a lot of users' hands, like yourselves. It's a technology that's been proven in across the industry now, I would say, well over 1,000 commercial tapeouts. It's a technology where we've seen productivity record after productivity record be achieved by designers being able to do more. It's also technology, I think, that gives us a lot of foundation for the future due to its universal applicability. And certainly, there's a connection between optimization, as Mark mentioned, and the new world of generative AI and large language models. And I think that chapter is, we're only beginning to see the early pages of that book. A quick disclaimer, we're going to be talking about a number of things today. It doesn't mean that all of these things are part of Synopsys products, and we're not going to be talking about Synopsys products. If you'd like to learn more about more information about AI and Synopsys products, certainly please reach out to your account manager or your AEs. But we're going to be talking about technology. A lot of it actually has made it into Synopsys products. So I'd like to start the talk by taking a little bit of a step back. Mark talked about Bayesian optimization. We looked at reinforcement learning. Today we're going to be focusing first on reinforcement learning specifically. But I'd like to take a step back and think about why do we really actually need that technology, right? A lot of times we tend to drive technology ahead of the problem. Let's take a look at the problem that's actually is leading us to these kinds of solutions. And I'm just picking up one design flow here. It's a digital layout optimization flow. In the center here, you see shapes moving around. That's an abstract representation of running certain tools and performing physical design tasks. It could be floor planning. It could be placement optimization. It could be clock optimization, IR drop-based optimization, what have you, right? So in any given problem, chip design problem for layout optimization, we have the space of a lot of inputs. And these inputs here, for example, starts with the logic itself, constraints that have to do with the area that we have applied the design. We also have a lot of the constraints that we capture in flow steps, in tool settings, overall guides that we insert into the design. All this goes into the design flow and the tooling. We also have large parameters, and those large parameters, for example, is the architecture of the cells that we're using. Our teams work for a long time to optimize standard cell libraries and then characterize them and push them into design flows as options. This is an expression of optionality. Of course, we have optionality inserted by PDK generation, so our foundries give us characterization of interconnects, metal stacks, parasitics, and so on and so forth. Now, all of those go into a physical design flow mill, if you'd like, and out the other end come a design. And the design we tend to analyze, again, as Mark described, based on a lot of metrics. Now, we have the very basic metrics here, like the total negative slack or the worst path. And now there are a lot of secondary and derivative metrics that have to do with the distribution of the paths, that have to do with local density. Tools use those metrics to locally optimize problems where those problems are linear, where those problems can be solved by optimization methods like linear descent. And at some point, an engineer like you will then have to take the results out of whatever is coming out of this design flow, analyze it, and unless you're working on a very simple design, try to work towards better solutions. So why is this happening? Well, it's happening because this optionality space we've created, all these green arrows and many more that you don't see here in this conceptual diagram, are contributing to a design space that quite honestly cannot be captured in its entirety with mathematical modeling. And that's where we go into the trial and error phase of chip design. Experience matters. It comes a decade at a time. And through experience, designers will then go ahead and tweak the optionality of the design towards an objective that they're trying to achieve. And that can happen locally, simple things, change some tool settings, or apply a design methodology, or offer feedback to other teams. For example, your foundry team in early stages of introducing a process, cell design teams, and so on and so forth. And this is an iterative process. It's a cycle that keeps going until our metrics converge to a desirable outcome, or until the design is deemed to be unfeasible and a major architectural change is warranted. Now, the effect of this is quite profound, particularly as the design complexity grows. So here, if I was to think of all these problems that I mentioned before as standalone self-contained problems, you can see that, for example, clock optimization has a lot of options, maybe 10 to the fourth of potential outcomes that you can have in a medium complexity design. Library cell selection is an even larger space, maybe 10 to the 6, as you're trying to maybe optimize leakage through cell selection. When you go to IR drop, you have a lot more parameters you're looking at, so the state space grows to maybe 10 to the 10. Floor plan, Mark picked it for a reason, is one of these areas where all the complexity meets you all at once, and it applies pretty much globally to all other parameters, 10 to the 14. And then when you start laying architectural considerations, performance, connectivity, issues that have to do with not only the manufacturing characteristics, but the overall output of the device, if you start layering the spaces, you can get into essentially more than the atoms of the known universe in terms of search space. So how do we go out and find solutions in the search space? I said before, experience matters. So that means that we have essentially established some techniques, right? Divide and conquer. So split the problem in layers, solve each layer separately, pick an optimal solution per layer, promote it to the next layer, and a lot of metric deduction, right? So if you look at the result of having this multidimensional search spaces, you will see something like this, right? It's a space that has essentially this continuous nature. It's very noisy, right? It's not differentiable, so you're not going to be able to apply a mathematical modeling to it. And once you get stuck in a local minimum or maximum, it's very hard to get out again. In other words, you want to be working multiple solutions all at the same time. The immediate impact to this is throughput, of course, right? It's very hard to identify causal relationships. If I change this, then this happens. And we only can evaluate a few variants of whatever search we're performing at any given time. And here is a diagram of an actual CPU optimization effort. You can see that while looking at metrics early on seems to converge towards our goal here of 100% of the metric we're pursuing, usually that metric is, of course, either performance or power, we get stuck in the middle where we spend a lot of effort and a lot of compute, but things don't generally change very fast. That's where we're caught in this absence of causal relationships. In the worst case scenario, we're just trying experiments to see which one is going to stick. And then through a lot of effort and, of course, a lot of data collection analysis, we sort of push through and we get to the goal. And that, of course, from an overall project management perspective means cost. And this is an analysis that was presented in one of our recent users group events where one of our customers presented that essentially through this loop of running, monitoring, and analyzing, there's a lot of idle time. There's a lot of opportunity for people to be doing more things, but they are either designing new experiments, or they're waiting for runs to complete so they can collect data, or they're actually extracting and analyzing that data in order to create more experiments. So this decision fatigue is leading to an effect here that I mentioned before. As we consider chip design as a journey from applications, from software, certainly in today's software-defined world, all the way to layouts, we have defined a number of data abstractions. And those data abstractions have allowed us to decompose the problem so that we can optimize it locally. And those create these waterfall effects that are also existing in software design. As you go from architectural design to structural to logic to layout, you see these discrete optimization domains, local visibility to next step only, and what we call limited design optionality. You can only try a few things at a time in this giant search space. And the other thing that's killing us is the difficulty to provide feedback from downstream effects to upstream effects, right? So we have these loops, we have no well-defined backwards flows, decisions are made at first level, effects only. And once we identify an optional solution, we lock it in. That limits our ability to explore the downstream solution. So that's why we care, and that's why reinforcement learning caught our attention as early as 2018 at Synopsys as we started exploring opportunities in reinforcement learning. So what is reinforcement learning? At a high level, very quickly, in the whole world of machine learning, you have essentially three categories. You have supervised learning, you have unsupervised learning, and you have reinforcement learning. The first two require data a priori, right? So you have supervised learning where you have the ability to have input data and labels and then train models that can help you do, for example, forecasting, prediction, image recognition. In the world of unsupervised learning, you can have techniques like clustering, dimensionality reduction. These allow you to take unknown data sets, unlabeled, and then perform tasks like recommendation, segmentation. In reinforcement learning, one of the most important things, and the reason why we like it for these kinds of chip design problems, is that there is no a priori data set. The data is actually generated, and is generated on the fly in the design environment and on the specific problem that you're currently working on. Now, clearly, you can seed it with learnings from prior experiences, but those learnings are statistical biases. They're not committed, and they're not captured as answers to any specific problem. So Mark showed a very similar picture before. We have, in the reinforcement learning paradigm, we have essentially one entity here we control, and that's called the agent. The environment, it can be anything that the agent can observe. So in my previous example, think of the chip design flow. And so the agent essentially goes through this loop of identifying, essentially building a trajectory of states and rewards. It starts with a very simple state up front, which can be essentially assume nothing, or through prior learning, assume something. Then apply an action to the system, and then observe, apply an action to the environment, and then observe the environment. And by applying enough actions and observing the environment enough, you are essentially trying to establish a probability function, a value representation between environment behavior and your actions. Knowing that at any given time, the action only in part may result in a reaction by the environment. And that's very, very important. And so the innovation here, I think is the most interesting, is that at any given point where you're actually observing the behavior of the environment and you're looking for goodness, that goodness comes over time. That's why this kind of technology, for example, has been very successful in game theory or playing complex games. Because your one move is part of the solution, but it's your sequence of moves that will lead you to your optimal result. So the idea is not to optimize any given answer. The idea is to establish policies that will allow you to optimize reward over time, ultimately getting to the end goal. And the end goal, for example, could be winning a chess game. In our world, the end goal is arriving at a better result, a better performance for your circuit. And there are many ways of doing this. There are model-based techniques where you're actually trying to create a twin of this environment, so you're actually not immediately impacting the environment because you're worried that the environment itself may respond to the action that you're applying and change its behavior. So it's not purely observation. And most interestingly, there are value-based techniques where we're actually estimating value functions. Given enough trajectories, we can actually map to specific known value functions or unknown value functions and then establish policies that allow us better results. And if you think about it from the point of view of a sequence of steps, you can start with an original position, and then by measuring the response of any given move that results in a new state, you can actually create search trees. And those search trees are exactly the capability that allows us to create solutions for large design search. Now, a few very important things. This kind of approach focuses on the design as a whole, so we describe long-term, big-picture objectives rather than tiny pieces. We don't try and control the process, we try and control the outcomes. We do not need a separate data collection step. Now, from the point of view of an EDA vendor, that is very empowering because, that may be a surprise, but we generally don't have access to your data. So it's important to deliver solutions that actually observe data as it is being generated in specific design environments, in the presence of your designs, and then being able to guide the exploration and search process with that data. And these environments, of course, can be very uncertain, they can be dynamic, they can include components that we don't even know exist. And yet we're able to observe, and through this loop, we're able to learn things about them that allow us to arrive at better solutions. Ultimately, with reinforcement learning, we can seek long-term goals overall while exploring possibilities autonomously. And autonomously is, I think, the operating word here. And perhaps the most famous example of this that everybody saw several years ago was the system that was able to teach itself how to play the game of Go, starting from zero knowledge and only observing outcome of playing the game against itself, reaching, of course, world champion status in a matter of days. Okay, so now we're equipped with this really cool new technology. What kind of problems can we go out and address? So we take our chip design flow and we wrap it in the system of actions, rewards, state transitions, And of course, we want to give it the ability to run a lot more than 2 or 3 experiments at a time. We give the ability and the cloud-based infrastructure for it to be able to run tens, potentially hundreds of experiments at a time. We give it the ability to cascade the results. So as it learns from early stages of running explorations, it can apply it to later stages, and so on and so forth. In other words, we take our waterfall model and we compress it down the middle. And we can give it any kinds of inputs, really, that can be numerically expressed and built within the environment of a chip design flow. What we're looking for is not one answer. What we're looking for is to maintain this optionality from the very early stages of design all the way through while we're exploring optimality. Not one stage at a time, but multiple stages at a time. And we're looking for those Pareto fronts, those places where we know that we cannot push any given metric, performance, for example, without truly suffering on another metric, power, for example. And here's a simple example of this kind of technology in action. Consider the problem where you have a design that meets timing. So you've met your performance targets, but you're trying to improve power. Now, that's an interesting one. Somebody will ask you, so how far can we push it? What's the lowest achievable power we can achieve for this design? Unknown, right? And that's why we need search technology. But in this environment, we can capture things that we know as designers, and we can prove through analysis, impact power. And then we can capture desired outcomes. We can capture leakage, for example. We can capture dynamic power. We can capture overall impact on timing in the form of TNS, or we can even calculate vectors based on distribution of paths. We can bring in secondary objectives that are important, meaning that we want to optimize power, but we don't want the design to suffer in other categories. We're going to push optimization domains to the very limit of their comfort zone. And we're going to run this, and we're going to see what happens when we try to beat an established solution that somebody has been working on for a while, trying to optimize, represented in the green dot. You know, leakage goes down, TNS goes left, so our solutions that we're looking for are down and to the left. And as we start seeing these tools in action, you can see how at the beginning, we're sort of all over the map. We know nothing about this design, right? We're exploring our trajectories. But as we start finding trajectories and tuning our policies, you can see a clustering effect. Remember, this is the performance space. We're not actually looking at the options. We're looking at the results that the options effectuate when you actually run the design through the exploration process. And this clustering effect is really what we want to see. We want to see that we've built a yielding design space that is actually performing the way we like it and ultimately gets to better solutions. Now that we have this capability, and we've shown it in one physical layout optimization example, what other things can we do with it? Well, turns out chip design is ripe with opportunity for these kinds of search-based optimizations, from the very early architectural explorations all the way to manufacturing. So we can apply it pretty much everywhere. So we looked at power optimization through cell selection before. Let's look at floor planning. So in the floor plan space here, we're looking at die size and optimize that versus performance. And essentially, you can see our sort of benchmark point with a little triangle. And you can see the exploration, and it looks a little bit all over the map. Again, we're looking at the performance space. But if you then start considering the effects of this, a Pareto front quickly forms, where we're seeing down and to the right this time, our size and area versus frequency reaching a point where clearly we're beginning to trade off between the two. And here we have, of course, one extreme where we have the smallest die achievable. We have the other extreme where we have the highest frequency achievable. And then in the middle, we have all kinds of interesting trade-offs. And the way to really think about these trade-offs is not about, what is the optimal solution for this design? Clearly, we want to find that. We want to think about the next design. We want to think about a derivative of this design. And a derivative of this design, for example, in this case, we're looking at the design that lies square in the middle of this Pareto front. But a derivative of this design may want to move up and down this Pareto front and achieve a different kind of solution mix. Now we have the data to be able to guide future exploration processes much more efficiently towards that level. Another interesting application of this kind of technology, of course, is verification. And at the beginning, people, when we started talking about verification, were thinking, wait, verification That's not an optimization problem, because at the end of the day, we want to know if there's a bug or not, right? There's no play. We want to make sure the design works. Yeah, however, we all know that verification is tackling an impossible problem. There's absolutely no way that you can actually go out and exercise the entire state space of a design. So modern techniques sort of look like this. You have an expert, again, decades at a time, that knows how to operate a constrained random environment, which means that through determinism, through setting switches in a test bench, those switches can be different seeds, can be different features of the design interfaces, then creates an exploration of a non-deterministic space, simply, of course, because it's driven by randomization, to explore as much of the underlying state space as possible, and through the strategy of hope, hit as many bugs as possible. There's no causality between what we do and the bugs themselves. We don't know where they are. Now, there are some proxies. There's some piece of new logic that just got introduced. Likely bugs are going to be there. There's logic that I've been shipping for 10 years. Likely bugs are not going to be there. But overall, as a technique, we're creating an abstraction. We're creating a proxy for this space, which we call coverage. And then by fulfilling the coverage, we try to arrive at a decision that this chip actually will work. Now, I can think of this completely differently. I can say, well, randomization was great, but what I really need is an army of designers, each of whom are actually experts at any given part of the design, and they'll write millions and millions of directed tests, carefully crafted, with the highest likelihood of hitting a given bug that they're suspecting. And of course, that's uneconomical. I do not have thousands and thousands of designs, and I don't have the time to write millions of directed tests. However, I do have the time to take an RL agent and formulate the verification problem as a reinforcement learning problem, and then train my agent to always take actions that will reveal more interesting states, that will maximize the likelihood of transitioning the design from a non-bug state to a buggy state, and reward this agent whenever they do so, and penalize the agent when they're wasted time running tests that exercise the same part of the design over and over and over again. And this, of course, can apply to all stages of verification, from early validation all the way to regression. In the interest of time, I picked regression because I think this is very, very interesting. This is an existing regression that was run as part of an experiment where nearly 250 or so unique tests are run with a variety of different seeds to achieve a coverage outcome. You can see the seeds or the unique tests on the y-axis. So the combination of the two results in several thousands of tests. And you can see how our constrained random test bench actually used our available compute. You can think of the area under this curve as available compute. You can see, for example, our existing test suite got very interested in tests between identifiers between 100 and 180 or so, right? Run a lot of incarnations of those tests, likely because somebody told them to go hit those tests hard. Now, consider the paradigm shift that I showed you before, where we put an agent in control of selection. We remove pseudo-random generation. We remove constrained random generation completely. We put the agent in control, and we allow the agent to build its own optimization trajectories, and then look at the result. How does this agent decide to use its available compute? Very different. Goodness, it didn't even run any tests between 100 and 181. Surely that's a problem, right? Surely this results in a lack of coverage. It got very interested in test 125 or so and 41 or so for whatever reason that it did. Look at the history regression, the way that coverage evolved over time, and the bugs that we found. And you can visually see that the area under the blue curve, quote unquote, significantly smaller than the one under the orange curve, which means it used less compute and it achieved an outcome, whatever that outcome was, in less time. So what was the outcome? Well, if these are our test seeds over time on the x-axis and our coverage evolution on the y-axis, our purple line sort of moved a little bit like this. If you're in verification, this should be very familiar, right? We hit a lot of coverage up front. Interestingly enough, just like our digital optimization example, then we hit a middle where we're just throwing stuff at it, and we just can't seem to get, more, right? We have now deeper states. Hitting them is hard. We don't know if we've hit them, so a verification, of course, could be tuned. Generally speaking, this takes, well over 1,000 unique tests to get us to, well, asymptotically, let's say, the target. And I kid you not, the agent is able to achieve this with just a few passes of the suite itself, right? Why? Because it's much more intentional about it. It tries to do exactly what we wanted to do because it actually scientifically goes about fulfilling that mission. And now, of course, you have a lot of time. And what are you going to do with this time? You may say, well, you know, now my nightly regression is done very, very quickly. Why don't I go and add more tests and add more targets? Well, great. We can do that too, because by building a sort of a probabilistic model of how state space behaves, we can go ahead and propose new coverage and build up the coverage model so we can use that extra time to do more, right? So lots of great benefits. And of course, I wish I had more time to talk about all the different applications, but the same kind of approach, again, carefully crafted to fit the search spaces and the desired outcomes of different areas, applies to many different problems, like circuit optimization, where of course you have a lot more corners, you have a lot more objectives you're trying to fulfill. Test, where you're trying to collapse the pattern space so that you can get out of the test earlier and spend less money doing test. Of course, 3D integration, right? Search space, design space exploration galore. Now we're trying to co-optimize multiple components for new metrics that we don't really care as much a few years ago, like, for example, thermal dissipation. But let's think about it a little deeper. What about the design itself? Meaning that, you know, we had all the state transitions of abstraction from applications to layouts. Clearly, through these examples, we can apply optimization at any given state. But how about the entire thing? Can I start multi-dimensional, multi-abstraction-based optimization and formulate problems that require operations at different levels? Well, my favorite one, I think, is HDL itself. So if you look at RTL, it's generally structured in layers, right? At the very bottom, we have instances that get mapped to synthesizable objects. From there, we go to functions where we have, you know, clock gating, we have structural components. Then as we move up, becomes more functional, order of operations, and loop rolling and unrolling, and structure. And at the very top, we have the microarchitectural knobs, right? The instruction set, am I going to use one ALU, three ALUs, different cache configurations, you know, the big ticker items. Not quite architecture, but microarchitecture. Okay, so what if we were to consider that any given RTL is a search space? I mean, I'm going to design something that will perform a functionality. Along the way, I'll consider myriads of potentials. Typically, I'll pick one or two to explore. But what if I was to capture all of them? Well, in an IP study that we did, that amounted to roughly 13 million permutations. All right, great. So what can we do with those permutations? Let's go back to our search. Let's say that we had one RTL. That RTL gets optimized through a baseline flow. Then that flow gets optimized again through our RL-based search or layout optimization only. So I'm keeping my RTL as is. I'm playing with all my toys to get the best possible power performance and area out of it. And I get this curve here, and I'm showing reduced number of points because clearly when I add more points, you know, I don't want to lose you. But we've identified some really good solutions. We got 7% better power, we got 5% better frequency versus where we started. So we're pretty happy with it. And maybe this is where our current Pareto layouts, our current Pareto lays in this current exploration. Now, what if I was to take some of these permutations in the RTL itself and evaluate them in the context of, again, the layout optimization flow? And now I get a lot more points. So clearly, changing the way that I wrote the original RTL and then putting it through the same optimization process and search can result in better solutions. Right? There are 20 points or so, and some of them are either higher performance or better power, or both. And you can see the overall sort of better performance we're able to achieve and a new Pareto front that has emerged. So the question then is, are these 20 different pieces of RTL? Are those 20 entirely different configurations? The reality is no. And I hope you can see this on the board, but if I bring in the information of what types of different configurations of RTL, of our original incoming RTL, actually got on the board as the best for this IP, there are actually 5 variants. And those 5 variants produce these 20 data points that push the envelope. Now, clearly, I explored a lot more than that. Now, interestingly enough, they come in clusters. So the little triangles on the bottom left, those were RTL variants that clearly exhibited more energy-efficient behavior. Here in the center, we have RTL that was neither here nor there, but is what I'll call balanced, meaning that it gave us a very nice spread of results. And as you'll see in a moment, when I bring in other metrics, it is actually giving us some really good, robust solutions. And then I have the RTL4 here on the right, which is capable of pushing the envelope further when it comes to frequency. Now, our RL identified those, and our trained policies now know the traits that come with those pieces of RTL. Now I can go back to the RL system and say, take this RTL and spend more compute in pushing RTL1 because RTL1 is more energy efficient. And the question then comes, okay, so is there one single variant that is the best? And that's the one that I should use for my design. Well, that's where we have to think about the other metrics that are coming in. So we were looking at power versus frequency, classic trade-off. But how about area versus routability, right? I also want this design to be compact. I want this design to be easily routable, or my tools will run forever, and ultimately I may not be able to close the design. Now, if I bring this data in, here's my original RTL. Here's RTL 1, 2, 3, 4, and 5. You can see how this becomes now a multidimensional problem. And I haven't even brought another 20 or 30 metrics that I'd be interested in. And if I look at across the board, if I was to reward myself for the best possible design, actually, that design is not any of RTL 1, 2, or 4 that I identified earlier. It's 5. And RTL 5 gives me the middle ground. Now that I have the middle ground, I can decide for future derivatives of whatever I design to push it in any given direction. I can say, go towards power. I can bring up my characterization map of design variants, and I can, if the animation worked, I can push it. Apologies for that. Let's see. Yeah, you can see there's an animation step missing, but you can see how I was able to push past the Pareto front by spending more compute towards RTL1 versus other variants. If I want to go towards frequency, same thing. I can pick RTL4 and I can push it towards my compute towards those areas. And then area, I can bring up my area and routability. And here too, I can go down into the left and achieve a better result because I'm again investing more compute and more exploration, specifically in the traits that I now know give me the result I'm looking for. Okay, so through this example, we can see how we can apply the optimization paradigm not only in specific design abstractions like layout, for example, but cross-design abstractions. In this case, we looked at how we can take pre-synthesis RTL all the way down to layout and create a hierarchical search system that allows you to consider the relative benefits for, again, for PPA in this case, across the entire abstraction stack that we traversed, from functions to gates to layouts. So, okay, great. Where do I go from here, right? The RL-based optimization paradigm does have some limitations, right? The first, of course, limitation is that you have to define the search spaces, right? You cannot give an RL system realistically, economically, your entire design and say, go and come back with the best possible design you can make. You have to bring your expertise in defining the search spaces. In the example we just looked at, this is creating design variants. And creating design variants and capturing IP that can operate in different kinds of conditions can be very high effort, right? One effort is verification. So if it takes me a long time to verify one implementation of one RTL, and I showed you 20, does that mean I have to spend 20x the effort to actually verify all of those different kinds of RTL? So generating well-behaving, validating optionality is a challenge. And then, of course, the other challenge is, throughout this whole discussion, we're actually running the entire design flow. We're getting a lot of data generated, but as you very well know, running steps like place and route can actually take a lot of time, right? So my evaluation of data points compared to, let's say, you trying to play the game of chess where you get multiple evaluations per second, perhaps thousands. Here we're getting data points in the order of a few a day, right? So completely different order of magnitude. Which leads me to my last part of this talk today, which is, where does a reinforcement learning, again, a technology that's been well validated, go from here? What is this opportunity space that we see evolving? And if you think about it, I love this chart. Thank you, Stanford, for creating. I've reused it here. We can start thinking of our ability to capture all these kinds of design journeys that we're taking with RL, all this data we're generating on the fly, doing different designs, capturing it and in data sets, and then using these data sets to train foundation models. And those foundation models now can actually be adapted to different techniques and different kinds of tasks. They can help us with debugging, as Mark mentioned. They can help us with design analysis, highlight things that we don't need to do by hand, even help us with identify strategies and orchestrate our design environments. And they can do it in natural language, which gives us a much higher bandwidth interface than painstakingly having to design search spaces and define them through languages like Verilog, for example, System Verilog. Now, if I have this background and I start looking at how RL gets augmented, here is a summary, right? RL for optimization uses tool engines to create and evaluate the design data. That happens on the fly. It's accurate because all the data comes out of tools that you use for tape-out ready designs, so they're validated design flows. It's overall slower because it has to run these entire flows and collect the data. And it's what I would call semi-automatic, meaning that it's autonomous in exploration, but it requires that you actually describe the design spaces and you describe the outcome metrics, and the overall performance of the system is tied intrinsically to how good a job you did in defining those spaces. Now, if I look at generative AI coming in, here we don't generate data on the fly. We actually have a captured representation of history from prior journeys. We can be speculative because we have now access to results that come directly from executing inference flows and neural networks rather than entire design flows to seed our systems. So it's very fast. And then it is highly autonomous, right? It is capable of traversing our data abstractions very, very quickly. So, and then help us explore this optionality that I was talking about before, right? So RL is very good at achieving optimal solutions in known spaces, and then generative AI is very good at creating spaces. So the two are actually very symbiotic here. In fact, they create a virtuous cycle between creating and analyzing that can be extremely powerful. Going back to our question, how do we create design variants? It's all about optionality. Give us more things to explore. Evaluating is all about optimality. They help us figure out if those things that you gave us, those options you gave us, are actually leading to optimal solutions and feedback. So if you think about these challenges, we see very interesting things in generative AI, and I'll mention some research that we have done at Synopsys, and Mark has done a lot of work here, and other folks have done a lot of work here as well. So the first one is, design variants are, in the example I showed, are RTL. Well, what if we were able to generate RTL, and what if we were able to generate RTL that is already functionally correct through formal techniques and test-based techniques, but take away the high bandwidth problem of actually generating RTL to evaluate, and substitute for RTL other kinds of abstraction, design abstractions. This gives us now a very powerful way to go out and create spaces to explore. And in this paper, which you can read, it's available online, we explain how you construct data pipelines to train the system, how you go through LLM fine-tuning and adaptation to create a proper training pipeline. Most importantly, how do you evaluate it so that you have high confidence that when a new design is presented, you can actually get high quality RTL. And then the feedback loop that allows you to enrich your data set and improve future design versions, which is also can be used for training other kinds of systems. So this is one vector where we see a lot of value. Another vector is in the optimality, and this is to evaluate the quality of the different options that you provide. And here we see some very interesting things that we've been able to achieve with graph neural networks, graph convolutional networks, and upcoming new capabilities in the transformer space. And this, of course, allows you to take a very sequential and computation-heavy design flow and replace it with fast and nimble models. Of course, keeping in mind that it's a different tolerance that you're playing with, and you have to take into account, of course, the directional correctness versus the tape-out accurate kind of results that you get out of running a complete design flow. But if you do that and you do that well, this is a paper we're going to be presenting at ICCAD very shortly, you can actually achieve very highly correlated results at significantly faster turnaround time. So here, if you look at the chart on the bottom right, we take a synthesis place and route flow full physically aware, and we are able to execute it to sufficiently good QOR for the purpose of exploration, hundreds of times faster through these techniques. In the future, I see all these things coming together in neural networks that can actually encompass not only the transformation capabilities that LLMs have demonstrated in the context of language, but also the analysis capabilities and the quality of results capabilities that we're now seeing currently in the graphical neural network space. So in summary, I believe we have seen the first wave of AI-assisted chip design in reinforcement learning-based systems for optimization. These optimizations can be performed within specific abstractions or can also be performed up and down the data abstraction stack in multi-stage, multi-domain, multi-abstraction optimization. As I said, this has led to a very important adoption here across the industry and proven in production across the board. I see a runway for the next 10 years of solutions penetrating new domains and combining to give us new optimization capabilities. Generative AI is coming in and is opening up opportunities, and the opportunity here is to tackle the design process more holistically. In other words, be the orchestrator of the design process, even if today's generative AI doesn't give us the accuracy requirement that we have to produce fully AI-driven design. But as we speak, as we show solutions, the next plateau is reached. And the next plateau reached, of course, and expresses the next level problem. High-level planning. This is not something that today's generative AI technology has actually mastered, right? It's an unsolved problem. And it's going to be solved, but it's going to be solved through reuse and leveraging past experiences. But without high-level planning, we cannot actually create these kinds of frameworks that can tackle the design process more holistically. Fast assessment of design quality for functional correctness remains, of course, to be a tall order. And while these techniques get us closer and closer and closer to having more autonomy and higher performance, more research and more work is needed to get there. And the good news is, I think Mark also showed that in his last slide, the pace at which technology is evolving, new publications, and then the application of technology outside of chip design space, in the chip design space, are giving us every reason to be very optimistic about the evolution of this technology. Thank you very much.
So I want to thank you, everybody, for, of course, sacrificing between quotes your Sunday morning to come listen to me. I'd like to present the new kid on the block, if you will, LLMs. I consider it like a 7-year-old, and I'll show you a little bit along the way why. So, of course, thanks Stelios and Mark. Tough acts to follow. I'll do my best. Bear with me. So, what I'd like to do is I'd like to first talk about LLMs. From a user's perspective, I'll try and give a conceptual understanding of how LLMs work, such that it becomes easier to understand how we can apply them in our daily life. But of course, this is mostly interesting, of course, here in chip design. Then I'll talk about retrieval augmented generation, was already briefly introduced by Mark, and I'll really show how retrieval augmentation is almost a necessity, or really an LLM without retrieval augmented generation in the application of EDA would be unlikely. And then last but not least, I'll talk about how basically, or how in essence the LLM and RAG just form the building blocks of AI agents or future AI agents, which then Mark and Hangchan will talk about more in their talks after the coffee. I need to find the... here it is. Okay, so an introduction to LLM. So what's an LLM? Well, you may be familiar, of course. It's a neural network. So like any neural network, you have a bunch of layers of weights with interconnect functions. Only a few hundred lines of code describe the architecture. But, or not but, and also you have a bunch of weights, a bunch of parameters which are learned during the training process. Now, where LLMs actually, differentiates from many other deep neural networks, deep learning networks, is that they're big when it comes to the number of parameters. Even though, there's trends there developing where, LLMs are getting bigger in a way, but at the same time, we keep proving that smaller LLMs can achieve similar results as bigger ones. So, there's definitely very interesting developments there in the industry. LLMs can be open or closed. I think that's interesting to realize. They can be open and closed both in terms of the weights as well as in the architecture. So, for some LLMs, the architecture is made public, but the weights are kept private. Other LLMs, they're both available. And there's sort of two threads in the industry now, where Meta is more going for the open source type approach, and an OpenAI, well, yeah, they used to be open, but they're more trending towards closed now. If you look at the training, it's interesting in that the amount of time and data and compute effort needed to train LLMs is very significant. So for example, for Llama 3.1, we're talking about a training data set of about 10 trillion words. It takes about 60 days to complete the training. It takes about 20,000 NVIDIA H100s, which I checked on Amazon yesterday, go for about, I think it's about $28,000 a piece. So you can compute the investment needed in order to be able to train a model. So, if you take an H100 at about, maybe $1 an hour, it's probably going to be a little bit more. Yeah, you're talking about a $30 million investment in training a model. Models can be quantized, which means that the weights can be compressed, and that will enable you to, sacrifice some of the accuracy and actually run it locally. So here's an example where we use an LLM for code generation. Now, what's interesting, I think, is that if you're talking about, using LLMs for chip design, many people I talk to, the first thing they think about is actually RTL coding. And of course, that's an application. But if you really think about it, the LLM being an assistant, the LLM, as probably everybody's aware, also can make mistakes like a human being. It can hallucinate, we'll talk a little bit more about. It's my belief that actually the low-hanging fruit for LLMs really is in the area of verification. the design, the RTL coding is close to the heart of companies. It's where they differentiate. It's also where the majority of the complexity lies. But if you look at the verification is, a little bit of a necessary evil, a very necessary evil, of course. There's many more lines of code in verification. Typically, a test case addresses one specific or more specific area you'd like to cover. So I really think that verification is a very good starting point. And what you see here is that we're actually using our tool called RapidGPT to, based on a single line instruction, like, I need a UVM test bench for a UART, just as an example. You can see that the chatbot, if you will, answers with like, okay, what are the specifications? Tell me a little bit more. So we're answering that. And you can see that the LLM, like a human being, is able to fill in a lot of the blanks, giving you over 200 lines of code. So really a starting point, a flying start you can use. It can really save you from, having to do a lot of typing and hence, increase the productivity. Not only that, I think an LLM can also help in, besides improving the productivity, if it helps you think outside of the box, it can also help you in increasing the quality of the end result. So where do LLMs fit in? Of course, in the domain of artificial intelligence, machine learning and deep learning, we already spoke about that. Generative AI, Stelios touched on that, obviously. Now, and LLMs are also part of, what's referred to as natural language processing. And I'll go a little bit about the history of natural language processing in the next slide. LLMs need to not necessarily be generative. You can also have LLMs which are non-generative, non-creative, but more analysis-type models. So a little bit about the history of LLMs. And maybe also natural language processing, actually. If you look at natural language processing, then in the 60s, MIT created a program called ELIZA. And this was, I would say, the first, at least from a software perspective, true attempt at, interpreting and parsing, if you will, natural language. It was rule-based, if you're if you were around in the 80s, you may remember the textual adventure games, right? You are in a forest and you see a box on the ground, what would you like to do? And you would enter open box or pick up box, right? Look inside box. So you would interact with the agent, or what do you call it? Now, then the recurrent neural network, which effectively is a neural network with a feedback loop, with an internal state, was proposed in '72, a long time ago, where really, the intent is to apply a neural network towards sequential processing. Now, it took till 1997 for really the recurrent neural network to truly, made to be applicable to natural language processing in the form of long short-term memories. And long short-term memory models would effectively, adjust the state based on past information seen in the sequence. So it would remember information from further back, which was deemed to be relevant towards predicting the next, element in the sequence. And that leads to the question, of course, which information do you decide to retain and which information do you forget? And that effectively gave birth to the whole, attention mechanism type principle, which we'll talk about later. That led to the paper, Attention is All You Need, which really, in my opinion, is the birth of the LLM as we know it today. So hence, my statement about LLMs being a 7-year-old kid, right, at the moment. Now, long story short, if you go through the ages, you can see that the transformer took flight. OpenAI produced a number of GPT models. You can see how they increased in number of parameters. One interesting data point is in 2021, Codex was introduced, and this powers GitHub Copilot, which you may be familiar with. And also, just last month, Meta introduced Llama 3.1, which I think is also interesting in that Llama is a much smaller model than GPT-4, and it reaches the performance and sometimes even exceeds the performance of GPT-4, showing that the sweet spot size of LLMs is still undetermined. More about use cases. Mark already showed some of that also. We spoke about, of course, using LLMs for coding and verification. But you can really think about many more use cases, because an LLM is like an assistant. So, it can help you with, for example, architectural exploration. You can ask a question like, what do you think is wrong with my specification, or what's missing in my specification? LLMs are really good at sort of thinking out of the box. As a human being, we tend to think down a certain track, right? You can think of IP integration, we'll come about that. But also LLMs can help you interpret information. You can envision having an LLM know about your IP catalog, so you can query it. You can use it for onboarding new engineers. The engineers can get up to speed much faster because they have this online assistant available to them, which they can ask questions about, your company policies when it comes to design, your design rule coding guidelines, you name it. And then last, also, you can envision using the LLMs for automation, we call it boring task for victim to neglect. Nobody likes to write documentation. Well, an LLM, based on all the knowledge you can feed into it, with RAG also, we'll talk about it, can actually generate the documentation as a, probably not your final documentation, but as a starting point where you can be assured that all the ports are mentioned, all inputs, outputs, state machine is explained, etc., etc. So how do we use an LLM? How does it work at the core? So in a way, an LLM is a next word predictor. It's a next word completion type engine. So you feed it with, in this example, the quick brown fox, and based on the training information, the LLM, associates the earlier sentence with the next word. Now, this is at the lower level. At the higher level, you're probably familiar interfacing with a ChatGPT type chatbot. It works with prompts, where you issue a prompt, and generally a system prompt is issued first below the surface. The system prompt really, tells the LLM how to behave in general, should it be an assistant, and what type of assistant. So it's like role play, what is the context, etc., etc. And then as a user, you ask a question and you go into a dialogue type of approach. And with every dialogue, the context window, as it calls, grows, where the LLM has a limit on the context window it can address. And hence, at some point, you run the risk of, the context window overflow. And then there's many, many implementations you can choose to adopt in order to make sure that the quality of the responses still remains, the way it should be. This is important to mention, though, because in the EDA domain, of course, where we're used to interpreting code, the context window overflow could become a problem. Talking about prompts, it's important to look at prompt engineering. It's a little bit like garbage in, garbage out. I mean, the power of an LLM is that it can fill in the blanks, just like a human being, right? But at the same time, if it fills in the blanks in an unexpected way, you're not going to get out of the LLM what you want to get out. So it's important to really, use the LLM or prompt the LLM in such a way that you get most out of it. And this really comes down to describing the task. What do you expect the LLM to, to do for you, right? The better you can describe that, the better of a response you get. Instructing the LLM, for example, tell it what you'd like it to do, but also give it examples what you don't want it to do. And last not least, also the context. So, who's the target audience for the response, but also give it more of a, point of view you'd like it to adopt, etc., etc. And actually, Hang Chan will talk more about prompt engineering in her presentation this afternoon. So a little bit, how do they work? Well, first, there's the concept of tokenization, which really means that if you have a sequence of words, you need to give numerical value to those words. Now, they're actually not words, they're actually tokens. So vocabulary is built. And in the case of, for example, GPT-3, that's a vocabulary of 50,000 tokens, 50,000 words or parts of words, for which every token has its own ID in a database, which is then leveraged. So you can see an example of, what is the tallest building comes down to 6 tokens. Now, next in the model, there's the concept of embedding. And this basically means assigning meaning to those words in the vocabulary. And that meaning is actually a parameter in the neural net, which is trained during the training process. And that meaning, you can really see there's 2 aspects to it. There is the meaning of the word as such, right? But also the relation of the words to other words in the vocabulary. And that meaning is, if you will, is stored in a vector with multiple dimensions. So every token is represented in many different dimensions. And let's see, I think, there's over 12,000 dimensions for GPT-3. And the model effectively learns, for each dimension, what it assigns meaning to each dimension, if you will. So if you take an example, if you take the words book and worm, which are 2 tokens, right? They're very different, but there's also the concept of a bookworm, which are still 2 tokens. But they all of a sudden, a bookworm is neither a book nor a worm, right? So you would expect for a bookworm that the embeddings of the 2 tokens will actually be close in at least one of these 12,000 dimensions after training. Because even though a bookworm is something different, they share, the word book and they share the word worm. Now, what's interesting is that, they can be stored in a vector database. So if you look at it from a vector perspective, you can actually sort of envision doing computations on them. And a very popular example is, I'm not sure if you've ever seen that, but it's the example like if in vector space you take the vector embedding for a king, you subtract the man aspect of it, you add the woman, then you actually come to the point in the vector space which is for the token queen. So I always think that's a very cool example. Now this shows an example of embedding. So you can see that the tokens are translated to token IDs, and that for every token in the sequence, there's this embedding. Now an embedding only captures the meaning of the word and the relationship with other words in the vocabulary. But if you look at something like, 2 sentences, swing the bat and the bat flew at night, then the meaning of bat is very different in these two sentences. So the true meaning in the end depends on the context. And this is where attention comes in. So attention is a mechanism where you basically, you take the embedding vector, and through a neural network principle, you bring it to a next sequence of parameters where you actually capture the association of words with the embeddings. So you can see an example here on the right side. The doctor asked the nurse a question, and then the next prediction. And you can see that the model says like, well, if you use the word she, then the next prediction becomes said. But if you use the word he, the next prediction becomes asked. So you can see that actually in this case there's bias in the model because there's this association based on the context, even though if you read it, it's ambiguous, that if it's a she, it must be a nurse, if it's he, it must be the doctor. And that's also one of the problems of LLMs. We'll talk a little bit about that later. So next then, is the transformer truly the network? Now, without going into depth here, you can see the tokenization, you can see the embedding. There is a positional encoding to have the neural network keep track of the location of the word in the context window. One thing here interesting to mention, so this is from the Attention is All You Need paper, is that you can see here that there's an encoding part and there's a decoding part. The encoding part basically analyzes an initial input and feeds the analysis, if you will, into the decoder part. Now you can have LLMs which are encoder only, so they only do the analysis of the input parts, and you can have decoder only models, like a ChatGPT, which is really more like a chatbot. So a little bit more about the training. How is an LLM trained? So they're generally speaking, there are three or at least two, I guess, stages to it. So first of all, this is often referred to as semi-supervised learning, where supervised learning is really using human-provided labels. What's interesting about training LLMs is that it actually trains on unlabeled data, even though that's not entirely true, because if you feed the training process with text, which can come from the internet, for example, Wikipedia or Archive or other repositories. If you feed it with text, then actually you simply say like, okay, the label you're trying to predict is the next word in the sequence. So as a result, the result of pre-training is really a base model which is good at predicting next words based on the previous words. It has good language skills. But at the same time, if you take a base model, or sometimes called foundation model, and you would use it and you would ask it, for example, like write a survey about LLMs, then it could be that it tells you like it completes it with like make sure it's not more than 100 words. And of course that's not really what you want, because you would want the LLM to actually write the survey. Now, for that purpose, there's the fine-tuning stage, where the data is actually labeled by human beings. And you can think of the human beings giving examples like, text classification, Q&A, such that it becomes more an assistant, summarizing text, etc. And that's actually what turns the LLM, or, if you think about a ChatGPT, it really turns it into a conversational assistant, like a Q&A type machine. And then stage 3 is reinforcement learning through human feedback, because it's a lot of work, of course, to fine-tune the LLM during the training process using human-provided data. OpenAI proposed a methodology which is commonly used, where you use the LLM to propose multiple responses, and you actually select the best response and you use that for fine-tuning the model. Now, LLMs are not, they're not a solution, a miracle solution. They have their limitations, they have their challenges. Some challenges can be overcome, but there's some concerns that really need to be addressed still. So one, of course, is that they are not good in math, logic, and reasoning. Also that they show bias, as we were talking about earlier. There's also the censorship discussion. I mean, should models be censored? Yes and no. yes or no. For example, if you ask an LLM like, how do I build an atomic bomb? Is it okay for it to answer? Or do we say like, well, maybe we don't want to go there? LLMs also, they only know the knowledge of the time until which they've been trained. So that can be addressed by RAG potentially, so I'll talk more about that. They can hallucinate, I think everybody's familiar. They can convincingly tell you why something is the case, and it sounds very convincing, but it just isn't. There's concerns in the industry about cost, of course, associated with inferencing, the compute costs and associated power of LLMs. There's legal concerns. Is it okay to train LLMs on copyrighted material? Is that fair use or not? There's malintent, what about LLMs being deployed or generative AI being deployed for, causes we don't want it to? Workforce descriptions. And, of course, ultimately the discussion on, what if the AI would start thinking for itself? Well, we're not there yet, but... so a little bit about the future. So there's discussion in the industry on, having LLMs potentially fact-check themselves by, looking at fact sources and making sure that the answers actually make sense. There's mixture of expert approaches where you can envision, having multiple LLMs be, together forming a higher level model, where you have an LLM on the input classifying the problem and call it delegating that problem to another LLM, an expert LLM for the solution. Of course, there's multimodality. We'd like the LLMs to know about voice, image, etc. Reasoning we could talk about, but in the interest of time, I'll continue. Context windows are very, very important when it comes to RAG. We'll come to that. And also the concept of extending LLMs with external memory. So that brings us to RAG. So RAG stands for Retrieval Augmented Generation. And it was a technique proposed by Meta in 2020, where you really enable the LLM to look up information which it can use when it presents its result. So you can effectively leverage data which the LLM was not originally trained on. And the LLM then acts on the combination of the input prompt, which is your question, with the additional information which was brought into the prompt. Now, why would you like to do this? Well, it's interesting, I think, to realize that the vast majority, it's estimated over 95% of the world's information, the world's data, is actually not online, but is private. So it's really in the hands of individuals and enterprises. So a good example, of course, in our world is semiconductor IP. But also you can think of, your design specifications, your product information, your methodologies. I mean, you wouldn't want to, of course, publish those on the web if you're a company. So RAG gives us really an opportunity to overcome this problem by bringing the private data into the context window to enable the LLM to basically mix its general language abilities with, what matters to your company. It can also thereby reduce hallucinations. You're bringing in the facts, and the chance of the LLM starting to make things up becomes less. It can also offer a way to bring in long-term memory into an LLM. I already described the context window overflow problem. So if you can, if you would save the dialogue in a memory, you can bring in that memory as it's considered relevant in RAG, such that the LLM, considers it again. So this is how RAG works at a high level. So you can envision having a corpus of raw data where the raw data is divvied up in chunks of text, and these text chunks are translated into embeddings, similar to like I was explained earlier. These embeddings are stored in a vector database, and now you can use that vector database to do a semantic search. So you can basically find, based on the input prompt, which is fed in from the prompt from the user, translate it into embeddings, and you can do a semantic search into the vector database to bring in and to rank the results in a certain order of relevance. So for example, if the prompt would refer to a specific IP, then the semantic search will find in the vector database that there's certain IP which would receive a high ranking, and you would augment the prompt from the user with that information and then generate the response to the user. So here's an example. So for example, system prompt, we are a Verilog design engineer. The user says, propose a Verilog module which connects an AXI APB bridge to a real-time controller IP. So the RAG mechanism does a semantic search to see if there's any relevant documents triggering on these words, right? It's not a word by words, but a meaning, a semantic search. It finds that there is actually IP available. It brings in that IP into the context such that the tool becomes able to respond with a top-level Verilog connecting these two IPs. So then the last part of my talk is about what can we do to build around and build on this LLM and RAG. And this is also a little bit of an introduction to this section after the coffee break, where Hongchan and Mark will talk more about this. So here's how we look at the world as PrimisAI. And it's a little bit of a busy slide, but if you go clockwise, starting with number 1, I think it becomes clear what we mean, because it's essentially adding, call it layers of technology to the LLM plus RAG in order to create an agent, a bot, if you will, which is an expert in a certain domain. So starting with number 1, this is really the baseline LLM, which is able, to just do Q&A, like, tell me a joke. The next layer is really to make this LLM know about our world of chip design. So for that, we do what we call domain-specific adaptation. You can think of fine-tuning the model with, specifically design examples. You can also think of prompting the model in the proper way. You can think of a mixture of experts approach. So there's many ways where you can do the domain-specific documentation. So now you can ask a question like, I'd like you to propose RTL for the following specifications. The next layer is really the retrieval augmented generation, which we spoke about. So you really, give the LLM the ability to leverage in-house company data. It can be IP, it can also be, your product specification. It can also be your design style coding guidelines to make sure that the agent starts, proposing code which is adhering to your guidelines. Next is to enable the agent to use tools. Of course, as designers, we're used to using EDA tools, so why not equip the AI agent to use the tools under the hood, such that as a human being you can ask it, for example, I'd like to run the simulation and I'd like you to interpret the results, as an example. Now next is really, until now the AI agent has still been a little bit of a, call it a piece of software which you start and you ask it a question, and then when it's done, the software, you can turn it off, right? But what if the AI agent becomes more like a task in an operating system, where the agent is always there, it's always on, it's always perceiving its environment. So you could envision an AI agent which permanently looks at your design repository, and when certain things happen in your repository, like it notices that a bug was found, right? To just give one example, but there can be many, then it does something. So like a human being, right? You observe your environment and you may not do anything for a long time until you pick up on something, and then you go like, oh, wait a minute, I need to take action. So, this could be like, you can ask your AI agent, like, whenever a new bug is found, I'd like you to send me an email. Now, what's interesting here is that here the LLM, besides, taking design-specific tasks, it can also start taking design management tasks. Like as a project manager, of course, you want to know at any moment in time, how do the number of bugs track towards tape out? How does my PPA track towards tape out, right? So you can really think of the AI agent starting to take on project management type roles. And then last is, if you equip the AI agent with, with memory, it knows about all of its past. It knows, it's fully traceable also what it said to you when. So it knows what you asked, it responded, you maintain this in a database. You can apply a RAG-like principle to access that database. And now you can ask questions like, for example, when did we find the last bug, right? Or what was the last bug which we found? And it'll just, be able to answer that because it memorized. And you can even think of the AI starting to adapt its behavior towards the future based on what it learned in the past. So if you ask, if something is not in the coding style guidelines, and you would ask it like, for future designs, I always like you to use a negative edge triggered reset. Then it remembers that and it finds that you told it in the past, and it will automatically comply. So this is from the agent perspective, but what if we deploy the agents in a workflow where we really target at automating the workflow? You can think of a high-level task of what we do as human beings. We partition it, we do a divide and conquer, a separation of concerns, right? So you really say like, well, let's take these agents and specialize them in a certain domain, and then deploy these expert agents in a workflow in order to complete a high-level task. So in this example, you can see that there's a much more complex prompt where we'd like to do a design, and we'd like to create a test bench for the design. We'd like to run verification on that test bench, and also we'd like to do a code coverage analysis. And, dear AI agent, only come back to me when the code coverage is more than 99%, or maybe, when certain time is up. And you can see that in this case, the task will be given, the task will be given to a dispatcher. The dispatcher interprets the prompt and realizes that the first thing it needs to do is do the design. The designer has a rack with an IP catalog such that it can leverage the IP catalog. And when it's done, it'll tell the Git operator to check in the design into repository. The designer tells the dispatcher that it's done. The dispatcher tells the test bench coder to create the test bench, check it in, it's done. The dispatcher knows to run the regression. And based on the result of the regression, if a bug is found, it tells the designer to fix it. If the coverage is too low, it asks the test bench coder to add more tests. And if both the requirements are achieved, then it actually completes, it tells the user that it completed the task. So you can see that actually every agent here has its own its own context of what it's trying to achieve. So there are really multiple LLMs which are at work here. And then last but not least, this is my last slide. I'd like to finish by looking forward. Why I believe generative AI and LLMs are really, a revolutionary new technique brought to the game. Also linking to Stelios' slide there. And the way we look at the world is that if you look at a task in terms of a plan, do, check, act cycle, right? Like, you plan for executing a task, then you actually do the execution, you look at the result, you check the result, and based on, what you see, you either say like, okay, we're done, or you iterate, right? Then if you look at, where the human is needed, then it's mostly, as Stelios also indicated, it's mostly on the planning side. And this is where LLMs and generative AI are starting to change the landscape of the world. Because, traditional EDA, if you will, it would be good at, for example, fixing most of the DRC errors automatically, right? So the tool internally, without you realizing, is able to optimize without need for the human in the loop. But, fixing a logic bug, for example, that was very hard to do. Until today, it becomes now feasible to some extent. I mean, it's an assistant, but quite a few bugs can be addressed by LLMs. So if you add up the two worlds between traditional EDA not being good at planning, and now LLM-based AI agents actually starting to become able to address some of this planning, you actually get a new world where we are truly going to be able to take the human out of the loop or reduce the need for human involvement in ways we were not able before. Okay, and with that, I think it's time for coffee. Thank you very much.